The first video here for astrophysics, we're just going to introduce some familiar bodies, or reintroduce, I suppose, and talk about just the general structure of the solar system and some common terms that you've heard of probably, but just we're going to refine those definitions a little bit before we get started into the physics of everything. So a little bit of astronomy. Here are, well, formerly 5, now 4 rocky planets that we have in our solar system. These are a great set of images. Some astronomer on his website had these, and they're just absolutely fantastic. But anyways, we have these. These are the relative sizes of our planets. Okay, which you do have to know their relative sizes, and also their distance from the sun, or the order from the sun in terms of distance. All right, so we're going to move through here. All right, and we got Earth. It takes what, about 11 Earths, I think, to fit across Jupiter. And we're going to keep going here in size. Next, all of our planets compared to the sun. Let's just go back here for a second, though. These 4 planets in front of the 4 rocky planets, these 4 bigger ones are the gas giants, sometimes gas/ice giants. All right, atmosphere is made of methane and ammonia on the surface, but mostly composed of hydrogen and helium. Thought to possibly have rocky cores very, very far inside. But compare all of those planets to our sun, all right, and we pale in comparison. Obviously, Earth, I think, is about, we get about 100 Earths we can fit across the sun here, approximately. All right, so cool stuff here. But our sun, though, still is just a medium-sized star. We can compare it to some of the bigger stars in our galaxy, at least. And here, comparing it to Sirius, which is a binary star system, a famous binary star system, and working our way up here through the red giants and red supergiants. Okay, Betelgeuse, candidate for what might be the next supernova, and Antares as well. So, yeah, kind of gets ridiculous here. Compare that our sun is just simply the size of 1 pixel compared to these stars here. And I think it's Antares. I think the orbit of Mars or something comes out to like here in it. So it's absolutely enormous star compared to our solar system. So yes, you do need to know the order of the planets in terms of their distance from the sun. All right, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. My very, what is it? Geez, I can't even remember what the mnemonic is anymore. Right. What you do, you just need to remember their order, though. I think you can easily look up mnemonics online. Oh my goodness, I can't believe I forgot it, but that's okay. No matter. This will be a question on the IB test, I guarantee, or something close to it, and it's embarrassing if you miss it. But just to go through the planets really quickly, a great image of Mercury here. All right, I believe it was the Messenger craft that took some of these images. Now what this is a spectral image just showing what some of the metals are that are on the surface. The chemical composition is multicolored one. The real color one here is just this gray one. But what we have right here, this is really cool. This is what's called the Caloris impact basin. So right there is one of the largest impacts that's known on any planet in the solar system. So you can see here, this is an image that's about 1/4 of the size of the planet, so it's a quite large impact there. Venus, famous for its atmosphere being a high concentration of carbon dioxide, pretty much a runaway greenhouse effect is what we have here, along with incredibly intensely high pressures and temperatures. Many of the first satellites first sent there actually by the Soviet Union in the 60s. I think the first 6 that they sent there, they either malfunctioned or entered the atmosphere but ended up being crushed. They were not made to withstand what's effectively 90 times the atmospheric pressure here on Earth. Venus is a little weird because it's the only planet that exhibits a retrograde motion in terms of its rotation as it revolves around the sun. it rotates the opposite direction the Earth rotates for its day, is what I meant to say there. So, yeah, so this first image here is that of its atmosphere. Here is a infrared image, actually, of what its surface looks like. Or radar imagery, so not infrared, radar imagery. So that's taken by the Magellan satellite that was sent to it. So here we go. Big blue marble here, great image of Earth, of this one. Mars, wonderful image here of Mars. Spirit rover taking an image here of its west valley. Very, very light atmosphere there on Mars. You then need to know about the asteroid belt. Here is a great image of just all the documented asteroids that exist. Obviously, this makes it look much more dangerous than it is because these dots do not represent the actual sizes of the asteroids. All right. So, and plus those dots do not represent the sizes of the planets there. So, moving on here, Jupiter. All right, we get outside the asteroid belt. And it's 4 Galilean moons here I have labeled for you. All right. Not in real picture. This is just a famous picture showing the Galilean moons in their order of orbit from Jupiter is all. So there you go. Io, Europa, Callisto, and Ganymede. A wonderful image. This is one of my favorite images. I'm pretty much just showing you my collection of favorite images of all the planets. So that's what it comes down to. This is from Cassini, okay? This is just a great image of the sun behind Saturn. And yeah, this is a real image. And if I remember correctly, the only reason I love this image is that that's Earth right there. I'm pretty sure about that. So moving on here, we have one of my favorite planets to say this following sentence. Well, the only planet you can say it and make it funny. But you can see here that Uranus is on its side. Waka waka. So actually, seriously though, Uranus really is on its side. Its tilt in terms of its rotation is like 98 degrees, I believe, to the ecliptic, which is the plane of orbit around the sun. Yeah, that's always a fun one to say. Uranus is on its side. Neptune, next out there. So the other cool thing about Uranus, actually, quite seriously, is it was the first planet to be discovered after the Jupiter and Saturn had been discovered by the Greeks. So many thousands of years passed, and then William Herschel ended up discovering it in 1781. And then Neptune was discovered a little while after that, right? So we can keep making fun Uranus jokes. Uranus is wider than Neptune, but Neptune is more massive. So yeah, anyways. But that's it for the planets. That's what you need to know about them. There are a few vocabulary words that you need to be familiar with. The first is stellar clusters. Okay, stellar clusters are stars that are actually gravitationally bound. Okay, that are close to each other in space. So these are a couple from the New General Catalog, NGC 265 and NGC 290. Just a couple of images of stars that are very close to each other, and, kind of close together and form groups within space. Now, when we look up in the night sky, we've over time through Islam culture and Asian culture and Mediterranean ancient civilizations, have ended up creating patterns out of stars and naming them, for characters from different mythologies. We often think of stars, in the sky as being close to each other just in terms of how we can see them. But it doesn't mean that they're actually close to each other in space. So we have two different things here. We have these constellations, which are groupings based on what we see here on Earth, and we have stellar clusters, okay? So these are two different types of bodies, all right, that you need to be able to, or two different types of classifications or ways we organize stars, okay? But they're different, and it's important to sort of just establish this as one of the first things when we get into astronomy here. So stellar clusters, right, a group of stars that actually are close to each other, and stars and dust too, that are held together by gravity, gravitationally bound. All right. constellations are groups of stars, as we describe it, in recognizable patterns. In the sky. Okay, so quick few definitions here. Now, we have those out of the way. The structure of the solar system, I've given it to you guys there based on all the images that I showed you. But just a few notes, right, to make here. Comets are the only thing I didn't talk about. They're highly elliptical. They come from the Oort cloud or the Kuiper belt. Those are pretty much their origin. But just a few numbers that I want you to have here. Anytime we're dealing with the sun and the size of the sun, we often use our variable here with a circle and a dot in it, and that tells us that we're talking about the sun. So here I'm talking about the radius of the sun. This would be the subscript for it, 6.96 times 10 to the 8th meters. All right. And the mass of the sun, we'll do the same type of thing here. 1.99 times 10 to the 30th kilograms. All right. And then we also have one little number here that you need to be familiar with, which is the average distance from the sun to the Earth. Now, all planets orbit in an ellipse. The Earth's ellipse is actually pretty close to a circle, but it's eccentric. It's a little bit eccentric. I think 1% eccentricity or something like that. But the average distance that we use, okay, one astronomical unit, is just going to be equal to 1.5 times 10 to the 11 meters, right, or 93 million miles. So yeah, that's just going to be the distance between the Earth and the Sun, a common unit we use in astronomy. All right. So some other distance units that we will be using, okay, are the light year and the parsec. So the light year obviously is the distance a photon travels in a year. We talked about photons from quantum physics, okay, so nothing new there. So we know that this is really fast. We've talked about what the speed of light is. So 1 light year based on just our 365-day Earth year, okay, is the following. And of course, I'm using an abbreviated version of the speed of light. And we end up with approximately this many meters. All right, so parsec is something we're going to define more specifically later on, but this is also a common unit of distance, and it's approximately equivalent to 3.26 light years, all right, which is approximately 3.09 times 10 to the 16th meters. All right, both of these common distances. I'm sure you remember parsec from Star Wars and the Kessel Run, all right, and Han Solo bragging about having made it in, what was it, 12 parsec or something like that. And you may say, hey, that's a unit of distance. How can you brag about, you know, making a race in a distance? And the idea there is that it's a smuggling route that goes around some sort of asteroid field or black hole field or some sort of crap like that. And he was able to make it he took a dangerous route that ended up shaving a lot of time off of it, and it, you know, required a good ship or person piloting the ship, whatever the case may be. So yeah, anywho, moving on. Just some general distances that you do need to be familiar with. The distance between stars on average is about 1 parsec. Okay, we will define this later. Proxima Centauri, which is the closest star to us, about 1.3 parsec away. Distance between galaxies is about 100 kiloparsec. Okay, at least within a cluster, because galaxies cluster together, and then between those clusters, it's you know, about 2 or so megaparsec between clusters, or galaxies and other clusters, all right? So those are just some general distances that are good to know, okay? The last bit here that we're going to talk about are the motion of the stars in the sky. So, you know, we look up in the sky and we have some beautiful images here. we have the Big Dipper point, the Little Dipper here with the North Star at the end of the Little Dipper. And we have this image here taken, all right, of all the stars going around, you know, at some point in the night, a long exposure, all right. And really what it is just these constellations going around at night. But what you need to know about this, all right, these constellations, this is, by the way, all the constellations that appear at the path the sun takes in the sky, which happens to be all the signs of the zodiac, all right? So all the zodiac constellations end up in the path that the sun takes in the sky, which is why they're part of the zodiac. They were given a special place that way. But constellations in the sky move from east to west, just like our sun, based on our rotation, okay? All right, and the relative positions of these stars, in general, in terms of, you know, where we are here, they stay the same, okay? There is some wobble, and we'll get to that in a little bit, okay? So the relative position of stars and constellations remains the same. Okay? This is what the ancients would call all of these stars and their positions, the celestial sphere. Alright? And Polaris, at this time, remember we talked about the Earth having precession and wobbling in its orbit, so you know this is going to change. But Polaris is on, or at, the celestial North Pole. But it is moving. And it is moving over the same amount of time that our Earth is precessing. Okay? So that's it. That's pretty much what you have to know here. One more little thing here I want to show you. It's pretty cool. It is an image of this celestial sphere, if you will. All right? And what it shows is the path that the sun takes during the year. And so what we see is that this is, you know, wherever you are standing on the Earth, all right, you know, what you would see based on where you are, okay? And that's going to be cut off by wherever you are for the, you know, for the horizon. It's going to be, you know, changing there. But the idea here, right, the celestial equator is based on the North Pole, all right? The ecliptic is tilted 23.5 degrees to that, and where you are, okay, during the year and where the sun is going to be changes based on all of that, okay? So, yeah, that's pretty much it. Just showing where the sun moves relative to the stars in the ecliptic throughout the year.